Okay, all of these images on the screen here are different manifestations of what we typically call static electricity. Static, well, that'll be our first note, but static means what again?
Lacking in movement.
Not moving, right. So technically speaking, not all of these things are actually static electricity that we've seen. So lightning is actually those charges in motion rather than static, but the kind of the pre-lightning buildup is definitely a static electrical phenomenon. This is very similar. It's building up some charge. What we see as these little fingers are actually the movement of the charge of the electrons through the gas that's inside. And so technically what we're seeing here isn't static electricity either. The girl up here with her frizzy hair, though, is demonstrating static electricity because the charges that we'll talk about are gathering on her hair and, just like we saw in the lab, repelling each other. So they are not moving at this point. They could later on. So first thing, what is static? And as we said, it means still or not moving or not changing, which is a very important distinction. We'll also talk in this chapter about current electricity, which is what happens when that electricity moves. This occurs because of a buildup of electrical charges. What causes electrical charges? Does anyone remember from previous science classes? Yep, Jamie. Friction often causes a separation of the charges that will allow them to build up. That's the force that often causes this, but it doesn't tell us what is involved in the charges. So if you think you rub two things together and the friction causes charge to move, what's moving? What physically is moving from one thing to another? What's that? Yes, but I already said that too. What is charged? When you look at things like us or the pipes that we've been using, what are these made up of? It's not a trick question. What is everything around us made up of?
Atoms.
Thank you. Atoms. Everything is made up of atoms. What are atoms made up of? There are three things. Protons, neutrons, electrons. So if we take just a quick look at a very simplified model, what do those protons, neutrons, electrons basically look like inside an atom? How are they arranged? Yep.
All the electrons, like the ones that stay in the middle of the room.
Mm-mm.
One of them stays in the middle like this, and the other two circle around. Yeah.
Incorrect. The correct parts of that were middle and circle around. So the question remains, what's in the middle? If it were a cell, what would be in the middle?
The nucleus.
The nucleus. What's in the nucleus of an atom? Well, but say it out loud, Emily. Neutrons are. So we've got neutrons in here. I'm going to represent them with the open circles, but there's something else in here too. So we have neutrons in the center. What else is in the center? Now remember that what I said, the other part of what you said was wrong. So what does that leave? You said electrons were in the center. I said no.
A mass membrane?
No. No, we're not talking about cells, we're talking about the atoms. It's called a nucleus in cells and in atoms. Protons. So we have protons and neutrons. Protons are the positive things, neutrons are the neutral or non-charged. So a proton is the positive. Sometimes we just abbreviate it as a P plus. A neutron is a neutral, as the name implies, and we might abbreviate that with an N and a little zero above it. What does that leave going around in a cloud out here? Electrons. I'll just make a minus there. Electrons, which we abbreviate often as an E minus. So that makes up every single atom. Different combinations of those three are all that differ from one atom to another. And we'll learn once we get into chemistry what we can tell using the periodic table about how they go together. But essentially, that's the only thing differing one atom from another. Now, if you apply some friction to this, and you're rubbing two things against each other, so a good example was the fur on the PVC, you're rubbing the outsides of these atoms together, or at least getting them really close to each other. Technically not usually touching at all. What then can you change? What could you do to change the charge if you start out with something that's neutral, like this, and you rub something and put a charge on it? What must be changing about this in order for this to become charged? Looking at our model, what could change and make a charge? Well, normally speaking, in its normal state, an atom has the same number of protons and electrons, so the same number of positive charges as negative charges. What must happen for something to become charged then? A non-neutral charge. Yes. Maybe it gets more protons. What's another option? Could get less electrons. What's another option? That's 2 of the 4. Neutrons are neutral, so that's the only one that's not going to change our charge. But we said we could get, what did we say, more protons. More electrons, did we say? Fewer electrons, okay. So that kind of gives you a clue what else could change about this. And make the overall number of protons and electrons unbalanced. Okay, yep. More electrons or fewer protons. So if any of these changes so that the balance isn't balanced anymore, if it's not the same, then you get a charge. Now, if we look at this, when we rub two things together, it's the outsides of the atoms that are coming in close contact. That means the electrons, the shells of electrons. Because if we look at an atom and we made the nucleus the size of this ping pong ball, the rest of the atom where the electrons are would be about the size of Rochester. That's how weird atoms are. It's empty space. So we've got this shell of electrons around our ping pong ball that's the size of Rochester. We can't get to this ping pong ball. It's shielded too strongly. So all we can do is get to these electrons. So that means that takes off the table the adding or removing protons. We can't do that, not under any normal circumstances. So it means we must be changing the number of electrons. So with that in mind, let's go forward and look at the rest of this. If we put more electrons on something, we disturb that balance. What overall charge, positive or negative, would be on a material that we add extra electrons to? Must be negative. We're adding more negative things. If we take some of the electrons away, what charge must be on it? Positive. Because we still have the protons that are positive there, and we removed some of the balance. Okay, so that is kind of the rest of this. So it often, buildup of electrical charges, as we said, often comes from friction. Electrons can be moved. And I'll give you a sec to get all this down, and I'll pause the video. If we gain electrons on something, we get a negative charge. If we lose electrons on something, we expose a positive charge. Whether this happens one way or the other is kind of hard to predict. We can often see what the result is by measurement, but it's hard to predict, at least at this level. Some types of atoms pull in extra electrons much more easily than others, and some give them up much more easily than others. In the case where we were using the PVC and fur, we started out by saying that this makes the PVC negative. So that must mean it gained electrons from the fur. The fur doesn't hold them quite as tightly as the PVC does, so that when we rub them together, the PVC can kind of steal some of those, giving the PVC a negative charge. Now, when you rubbed the PVC with fur, you probably noted that this actually kept the charge quite a long time, and you could keep using this same tube for measurement. So if I hang it up here, I can use this tube for measurement for quite a while and still get a reaction from that side. Also, some of you noted a big difference with how PVC behaved compared to copper, and even noted a difference between these two materials. What is the primary difference when we're talking about electricity between these two? Yeah, Jim. Conductor. Do you know what that means? It flows through it. Plastics and glass and things are not. There are two main categories of substances that we're going to look at, or materials that we're going to look at with static electricity and current electricity, and those are insulators and conductors. Conductors are, as Jeremy very correctly said, materials that allow electrons to flow through them easily. Good example is copper, but really any metals are good examples. That's what defines what a metal is. It allows these electrons to flow. Graphite in your pencils is a good one. People are good ones. We often think of water as being a good conductor. Technically, if you've got pure water, it's not a very good conductor. But as soon as you add any other impurities into it, salt or dissolved metals and things often come in the form of different types of salt, then it becomes a very good conductor. That's kind of what we are. We're sacks of messy water. And that's why we're pretty good conductors. Our skin is actually not that good, especially when it's dry. So in the winter, our skin is dry, we tend to hold on to charge and we don't conduct nearly as well because it can't conduct through our skin. But once you get inside our skin, where we are all squishy and moist, then we're very good conductors. We're going to do some experiments with human conductivity later on, and if you've got like sweaty hands, that's actually a benefit for your conductivity, for how good of a conductor you are. The other category, this is actually really relevant. We got some strange behavior out of the copper, and we'll discuss more about that in just a little bit. And that's because it's actually really hard to build up static charge on some conductor like copper. Because let's say that I rub this fur on it, and I'm transferring charge because fur gives up the charge pretty easily. And so some of those electrons are going into the copper. But here's the thing, we saw in our lab that electrons repel each other. Like charges repel. So when I put extra on here, they just push each other apart. This is a conductor. So it can flow through into any other conductors like the big meat bag attached to it. Right? And then they spread out. So I'm not actually leaving any extra electrons on this copper. And it stays neutral. That's one of the last question in the conclusions of that lab is how could you get this to work a little more like some of the insulators? So let's talk about how insulators work. Insulators are materials that resist the flow of electrons through them. You can't ever quite stop the flow of electrons, but you can make it very difficult. So things like plastic, glass, rubber, air, wood, those are all really good insulators because none of them allow electrons to flow through easily. Because of that, if I rub, say, this plastic with fur and transfer some electrons off of the fur onto the plastic, they tend to stay there. They can't flow away into my hand. And since they're surrounded by air, they don't flow away into the air very easily either. They tend to stay exactly where I put them because this is an insulator. We saw how different charges built up on things interact with our experiment. And they interact because of something called electric fields. Electric fields are force fields around objects that have charges. If you bring two things that have similar charges, so both negative towards each other, what happened to them? Think of our lab with the spinning tubes. If I charge up this PVC, put it in the cradle, and then I charge up another piece of PVC the same way so that they have the same charges, what happens to them? They repel. Like charges repel. What if I brought something around like this acrylic that became positive, close to my negative? They attract, opposites attract. It's that interaction of these force fields. Opposite charges attract, like charges repel. So let's look at this from the standpoint of our lab. We first took some PVC, we charged one end with, I'm going to wipe one hand with my hand, or one side with my hand. What does that do, by the way, if you wipe it with your hand, considering what we just learned about charges and conductors and whatnot? So if I wipe this side with my hand, what's happening to any charges that were on this? They go into my hand, and then they can spread out because I'm a big conductor. So if I wipe off all the extra charges on this, not all the charges, remember, because there's still protons and electrons, they just balance now. What charge is left on that side of the PVC? Neutral, okay? But now I'm taking this other side, rubbing it with fur, and I told you without any proof, although it is true, that doing so puts extra electrons on that side of the tube. So if it's got extra electrons on it, more than normal, what charge does it have? Extra electrons means what charge? Negative. Electrons are negative, so extra electrons mean negative charge. I'm doing the exact same thing to this tube. So if I rub this end with the fur, it also becomes negative, and I bring two pieces both with negatives close to each other, and they repel. Okay, we saw that in the lab. If you rubbed, check quick in your lab, if you rubbed acrylic with fur, what did you find for the charge on it? Is it going to attract or repel the PVC? What'd you find? Attract. Okay, so it should attract. So PVC with the acrylic. I'm running out of charge a little bit on that pipe, but definitely attracting. So that would indicate that these must be opposite charges. I'm going to charge this up again quick. I'm going to do the same thing now with copper too. What do your notes say? What happens when I bring a piece of copper that I just rubbed with fur close to my PVC rubbed with fur? Should attract, okay? Definitely attracts, indicating copper must be what charge? Must be positive because we said that was negative. So here's one more. Now here's where the analysis part goes. I have two things that are positive. If I bring two positive things together, what should happen? They should repel. So I want to check that. And this is what a lot of people forgot to do in their analysis. And so we'll have some time today to finish this up. So I'm going to try and charge the acrylic. Charge my copper with the fur. Bring them together. And
It attracts.
it attracts. We broke
I
science.
throw money on the floor.
We broke science. Ugh. Even more confusing to me is if I take this PVC tube and wipe my hand across it, what charge does the PVC become? Should be neutral because I'm removing all of the extra charges that were on here. If this were positive, by the way, this would still work because I could donate my electrons to it. Electrons move on and off of us really pretty easily because we're so big. We don't miss a few. So big, at least compared to this. So that should be neutral. This should be neutral. If I bring two neutral things together, what should happen? Nothing. So let's double check that these are both neutral. Nothing. It's swaying a little bit. Try and balance that out. This is sort of what we started with. Nothing. Okay, so both of those are neutral. Now if I charge this, make it negative, what happens when I bring it close to a neutral thing?
No.
Oh. Oh. What? That attracts. Let's check this. So that's still neutral on there. It was just attracted to my negative thing. Let's try this. We said that the acrylic attracted to the PVC with fur, so it must be positive. If that's true, oh my gosh. That's attracting too. Oh my gosh. Okay, so the neutral PVC just attracted to both a negative thing and a positive thing. Okay, what's it going to do with the copper? Probably attract. I don't know.
What'd I say? Nothing.
Yeah, if I put it on the other side, though, it's not going to move it. That's just the sway from the string. It didn't attract. What does that mean that charge must be on this copper tube? If they don't attract at all, what charge must be on both? Must be both neutral, because we just saw that a neutral thing attracts to either positive or negative, but not to another neutral. That's what we saw with this copper the whole time, right? It attracts to anything except another neutral thing. Let's find out why. The key to this is something called an induced charge. What does it mean to induce something? Many of you have probably heard that term in more of a medical setting. Possibly. When have you heard the term induce? So what do you induce with anesthesia? What do you induce with it then? No, you're not inducing gas. What do you? Okay, let's think of other ways other ways in medicine. Okay, you induce a sleep, is what it'd be called. What else is induced in medicine?
Lying.
Babies.
Induce milk.
No. Antibodies.
It's babies. What is it? Well, how do you induce babies? What's related there? Nobody's ever heard of.
Offspring. The stairs.
Nobody's ever heard of inducing labor.
C-section.
No, labor, birth. Stop. When, in particular, if there's some reason like the pregnancy has gone on several weeks too long, or if there is some medical condition, the pregnancy or the birth can be induced, meaning that it's kind of forced to happen. You might induce a coma under certain circumstances, force someone to be in a coma. I don't know all the medical reasons for that one. But it all means the same thing. This means forced. So this is like a forced charge. When we've got a charged object close to a neutral object, we force a charge on that neutral object. We're going to see an animation that helps explain this, similar to something you've experienced before. I still have not brought balloons in. I've forgotten those. I'm going to do this. Let's see. Perfecto. But I do have this neat animation. Notice over here on the wall, so this is a wall. You know that if you were to rub a balloon on your hair and hold it to the wall, what is likely to happen? Sticks there, right? Well, the wall is normally balanced. It has a neutral charge. Same with a balloon to start out with. But when you rub two things together, say a balloon on your hair or this sweater, right? Let's say the sweater is normally neutral, but when you rub the balloon on it, it grabs onto a bunch of those electrons, making it negative. Let's look at what happens when we bring this negative thing close to our neutral wall. This is what we just saw with the tubes. It's separating some of the charges. It's repel. Well, and so this is negative, so what does it repel? The negative parts, the electrons. Now it's not going to completely separate them. The wall is an insulator, so charges don't move well on an insulator, but it can kind of push them away so that they spend more time on the other side of their atoms. And that's what this is trying to illustrate. If the electrons spend more time on the other side of their atoms, that exposes more of the positive parts here, the nucleus. And that would attract the negative balloon. This is what we mean by an induced charge, a charge forced on a neutral object. So it makes it look positive, even though it's still technically neutral, it just moves the charges around a little bit. What if I can't change this, the only downfall of this, but what if I could take some other balloon material, rub it on the sweater and have the sweater take off electrons? So this gets negative, this would get positive. What would happen? Well, how would it look different if I brought it close to the wall, if the balloon were positive instead? Would be repelled. You would think so. But it doesn't quite work that way, and here's the distinction. But that's the right kind of thinking. Over in our nucleus, in here, the center is really well shielded, remember. and it can't really move very much. It sort of vibrates in place because it's held in place by all of the atoms around it. So the nucleus part can't move. The positives will never be moving in our experiments. So what other option would there be for this wall to still attract a positive balloon? What else could happen inside the wall if it's not the positives moving? Can't really combine. What part of the atom can move? The negatives move closer. So instead of the blue negatives, our electrons, moving away, if this balloon were positive, they'd tend to move closer, making this look negative. Same thing happens with we had thunderstorms this morning. Same thing happens with that. The Earth is somewhat conductive, especially when it's wet, like with the rain. So if you've got a cloud above it that has a big negative charge, in the Earth below, it's going to push electrons away, making the Earth look positive in that section, and that's what eventually allows the electrons to flow in lightning. So they get down there and then they can spread out. We're going to talk a lot more about that spreading out in our future few experiments. For today, what I want you to do now is go back over your data and see, do I have any holes in it? A lot of people miss the analysis section entirely. I want you to double check some of those things that you thought were positive and figure out which ones are positive. Because if you bring two that are positive close together, what should happen?
Repel.
They should repel. So check which ones are positive and which ones have this induced charge on them. And then go back and rewrite your